Electricity in one shot. Let's master current, Ohm's law, resistance, heating effect and power, quickly and exam ready.
Welcome to Teaching Science. Have you ever flipped a switch in your room and wondered what exactly makes that bulb glow almost instantly? Or how your phone magically charges up the second you plug it in? Well, today, we're going to understand this entire electricity chapter step by step, in the absolute simplest way possible. No stress, just clear concepts. Let's get started. So think about it. What really brings an electrical device to life? See, just having a battery and a piece of wire isn't quite enough. We need a continuous, unbroken flow of charge. Without that constant flow, our screens just stay dark and our rooms stay unlit. It's kind of like a heartbeat for your electronics. Here's our roadmap for cracking this topic. We'll start with current and electric circuits, then explain potential difference. After that, we'll cover standard circuit diagram symbols, Ohm's law and resistance, and series and parallel resistors, before wrapping it all up with a complete chapter final revision. Okay, let's jump right into part 1, current and electric circuits. We need to lay down some basics here. Think about a river for a second. Just like water flowing down a riverbed creates a water current, electric charge flowing through a conductor, like a metallic wire, creates an electric current. It's literally the rate of flow of electric charges through a particular area in a unit of time. But hey, here's a fascinating piece of history, and it's a super common exam trick too. When electricity was first observed, electrons hadn't actually been discovered yet. So scientists just assumed positive charges were the ones moving. Because of that, today we conventionally say the direction of electric current is opposite to the direction of the actual flow of negative electrons. You definitely want to keep that in mind. So how do we actually measure this flow? Well, electric current, which we denote with a capital I, equals Q divided by T. Q is the net charge measured in coulombs, and T is the time. The current itself is measured in amperes, named after the French scientist André-Marie Ampère. And guys, major board alert here. You will very often be asked to define 1 ampere. It's simply the flow of 1 coulomb of charge per second. To measure this current in a real-life circuit, we use a handy little device called an ammeter. Now, looking at how this is all put together, you can see exactly what a continuous closed path looks like. Notice the path of the current here. The arrows point straight from the positive terminal of the cell, through the bulb, through the ammeter, and then right back to the negative terminal. And here's a massive exam tip for you. See that ammeter with the capital A inside the circle? It is always connected in series within the circuit. If you break this circuit anywhere, like say by opening that plug key at the bottom, the current stops dead in its tracks and the bulb goes dark. Moving on to part 2, let's talk about potential difference, which you can also think of as electrical pressure. So we know current is flowing charge, but honestly, what actually pushes these charges to move in the first place? To understand this, let's go back to our water analogy. Water sitting in a perfectly flat tube isn't going to flow anywhere, right? It needs a pressure difference, like connecting one end to a really high water tank. In an electric circuit, electrons only move if there's a difference in electric pressure along the conductor. We call this electrical push potential difference. Formally, it's defined as the amount of work done to move a unit charge from one point to another. Usually, a battery or cell provides this essential push by using its stored chemical energy. Mathematically speaking, potential difference, or V, equals the work done, W, divided by the charge, Q. Work is measured in joules, and potential difference is measured in volts, named after Alessandro Volta. So, putting that into perspective, 1 volt is simply 1 joule of work done to move 1 coulomb charge. Now listen closely, because here is a common mistake you absolutely must avoid in your board exams. While an ammeter connects in series, the instrument we use to measure voltage, the voltmeter, is always connected in parallel across the points you want to measure. Never forget that. All right, let's get into part 3, standard circuit diagram symbols. Look, in the board exams, you just don't have the time to sketch realistic little pictures of batteries and bulbs, right? We need a universal, quick language to draw these circuits. An electric cell is drawn as a long vertical line for the positive terminal and a shorter, thicker line for the negative one. A battery is just a combination of these cells connected end to end. Notice the plug key. It's super important. Brackets without a dot in the middle mean the switch is open, so no current flows. But brackets with a dot, that means the switch is closed and the circuit is complete. And finally, see that zigzag line? That represents a resistor, which is exactly what we're going to talk about next. That brings us perfectly to part 4, Ohm's law and resistance. This is where we finally bring voltage and current together. I want you to think about this for a second. If you increase the electrical push, that potential difference from the battery, what do you think happens to the actual current flowing through the wire? Does it go up? Does it go down? Or does it just stay exactly the same? Well, way back in 1827, a German physicist named George Simon Ohm answered this beautifully. If you plot the potential difference against the current for a simple nichrome wire, you get this perfectly straight line graph passing right through the origin. This brilliant visual proves that as voltage increases, the current increases linearly right along with it. And that, my friends, gives us Ohm's law. The potential difference across the ends of a metallic wire is directly proportional to the current flowing through it, provided its temperature remains the same. When we remove that proportionality sign to make an equation, we have to introduce a constant, and we call it R. So V equals I times R. This R stands for resistance. It's the natural property of a conductor to resist or oppose the flow of charges through it, and we measure it in ohms. But what actually makes resistance change from one wire to another? Here is a major board alert for you, so pay attention. Resistance depends on a few specific physical factors. First, it's directly proportional to the length of the conductor. Think of it like walking down a crowded hallway. A longer hallway means you're going to bump into more things, right? That's more resistance. Second, it's inversely proportional to the area of cross-section. A thicker wire is like a much wider hallway. The electrons have way more room to flow, so the resistance actually goes down. And finally, it depends on the nature of the material itself, which is represented by that little Greek letter rho, meaning electrical resistivity.
All right, let's look at part 5, series and parallel resistors.
In real electrical gadgets, we almost never use just one single resistor. We use multiple resistors, and we usually set them up in one of two primary combinations. Let's compare these two systems side by side. In a series combination, the resistors are connected end to end, literally like links in a chain. Because of this, the exact same current flows through every single resistor. So, to find the total resistance, you just add them up directly. Total R equals R1 plus R2 plus R3. This means your series resistance is always going to be higher than any single resistor in that chain. Now, in a parallel combination, the resistors are basically stacked between two common points. Here, the current actually divides up among the baths, but the voltage across each resistor remains exactly the same. The formula gets a bit flipped into fractions. 1 over the total parallel resistance equals 1 over R1 plus 1 over R2, and so on. Doing this actually decreases the overall resistance in the circuit, which is super useful. Okay, we made it to part 6, our complete chapter final revision. Let's lock all this in. Wow, we have covered an incredible amount of ground today. Let's do a 1-minute rapid-fire recap so you are absolutely ready for your board exams. Remember, current is simply the rate of flow of electric charges. Potential difference is the work done to move those charges. It's that essential electric pressure. Resistance is just the conductor's natural opposition to that flow. And please, never forget your device placements. Ammeters are always connected in series to measure current, and voltmeters are always connected in parallel to measure voltage. And here is your ultimate formula cheat sheet. You really want to lock these into your memory. I equals Q over T. V equals W over Q. Good old Ohm's law. V equals I times R. Your resistance factors, R equals rho times L divided by A. And for series resistors, total R is simply the sum of R1, R2, and R3. Take a mental snapshot of this right now. It is an absolute lifesaver. And that completely wraps up our explanator on electricity. I strongly encourage you to practice drawing out the circuit diagrams and try solving the NCERT textbook exercises using the exact formulas we just reviewed. But before you go, look up at the lights and appliances around you right now. Based on what you just learned today about how voltage and current divide, can you figure out if the wiring in your own house is structured in series or in parallel? Think about it. If you found this lesson helpful, please like, share, subscribe to Teaching Science, and don't forget to press the bell icon so you never miss our next CBSE Science lesson. Catch you next time.